still integration of vector fields.
Oh, you are in. Good.
Continued from last time. I didn't, just one lecture on the subject is not sufficient. So, the manifold, and we have a vector field on this manifold. Some nonlinear thing, maybe. Vectors, field of vectors. And we are interested in finding, at first, integral curves of the vector field. And I quite often will call such a curve gamma as a function of a time variable. And I always like to draw the time interval just to keep myself oriented where we are. So this is the time interval from some number A to B. And for me, I always have a base point, 0, in the discussion. And we are looking for a curve which is tangent to the flow of this field. So we're looking, in this case, say we have a base point here, x0. I mean, 0 goes through x0. We're looking for a curve that is tangent to the field. So this is somehow the map, a picture of what gamma could look like. And the condition that we have is that we go through the initial point. So gamma of 0 could be the base point that is given to us. And the velocity vector of gamma is at the point gamma of t, when I write here, of course, at the point gamma of t is the vector field at that point. The velocity vector, of course, is a tangent vector in the tangent space at the point of question. And anybody in applied science think of it as tangent to the curve. And that's what it is, of course, tangent to the curve. And the velocity vector, say at some point here, will be some vector tangent. I think it should be the same as the given field. So, in that form. Some confusion about the notation last time, so let me just repeat that we talked about. So in coordinates, so local coordinates in some coordinate chart. So I will always write, you can write gamma t if you want, but I want to remind you that gamma is a curve, so you can apply the coordinates to the curve and get a coordinate version of the curve, x1 of t through xn of t in the coordinate chart according to the curve. And so it follows that the derivative of the velocity vector, we all know this, is just the derivative of the individual coordinates. That's really a vector there. Okay, and it means that the vector field x, then in this case, in coordinates, is nothing other than, has to be these velocity vectors are the coefficients. This is the vector field coefficients, dx, dj. This is the condition of the curve. This is the condition. The condition is then, of course, in these coordinates. So the condition becomes, we did this last time, but I'm just reviewing it, that the velocity vector has to equal the coefficient vector of the field. The velocity vector at the point t equals the coefficient. Let's write this as a of t, a of x, not constant here, and that says then the statement is a of x of t. You see this is a vector equation, so that n equations for this, and with an initial condition, which is someplace here, here is the initial condition. Okay. So this is n ordinary differential equations with an initial condition. This is a standard question in ordinary differential equations. This is the standard linear ordinary. Let me remind you, sometimes this ordinary differential equation, you will see here, x point equals a of x and t. There will be two variables here, x and t. So it's a vector field, but the vector field is changing with time. Can you imagine? These are the coefficients of the vector field. So you see, let me just emphasize this. So another time-dependent vector field quite often occurs in applied problems, is namely this vector field x is dependent on a time t. So it's really a vector field which is changing with time. And so the ODE, the ordinary differential equation, is of the form x of t equals a of x of t and time. It will change with time. Time-dependent ordinary differential equation. I will speak about the existence and uniqueness solution conditions, what it really means. Solutions exist, they're unique and so on, but I will talk about that in just a minute. So the easiest example is a fundamental example of linear fields. So in this case, the manifold is just a vector space. And I've made big propaganda for complex vector spaces, but all the time here these would be real vector spaces. Real vector space. Okay. And you should make a picture of a linear field like this. Here is 0, here is V. And we know a field is obtained by differentiating along an affine line. And so you differentiate along the line which is given with base point V, and you differentiate in the direction A of V. So the field here, XA, is given at the point V by differentiating along this affine line well, maybe I should I'll just put it in here, V plus VA. If I didn't put the argument of the function, that's what you do. You differentiate along that line. Okay? So, at the base point x of V equals A of V in the tangent space at the point V of V. Depending on V, the field changes linearly. And now we talk about, I'm reviewing still, we talked about last time, the first beautiful example is A equals J in the plane, rotation through 90 degrees. Right? And we saw the picture of this, everybody just likes this picture very much. So this is rotation positively oriented through the plane, in the plane, in 90 degrees. Okay. So that means if you're, for example, here on the circle, well, think of you on the unit circle, maybe it's a vector of unit length. J of V is perpendicular to that. And so that means if you're differentiating along this line here, and you see obviously that's the same thing as differentiating along that circle there. So you view this line as being the tangent space for the circle we talked about. Now let me review one of the last remarks that I made yesterday. I love this remark, so I'm going to make it again if you don't mind. It's a beautiful remark. So we take the unit circle to this point 1, 0. So that's our base point, x 0. Now, a general theorem tells us that linear fields are integrated as above by one-parameter groups and these one-parameter groups are very simple-minded things, namely t, time t is the group element e to the ta, which is one parameter group in the general linear group. The headline for this lecture is the hidden group. The hidden group. You see, you would never think if you, and you've heard about differential equations before, I think everybody, right? And you've heard about ordinary differential equations before. But maybe you have not heard the propaganda about the hidden group. Right? The hidden group. That's the message today. Really the message I'd like you to leave this. There's a hidden group in the subject of ordinary differential equations. Here the group is not so hidden. The group is just this one-parameter group e to the at. So the e to the t, gamma of t will be then, the integral curves are simply e to the ta times the base point x0. So you obtain the solution to the integral curves, the solution to the ODE by an R action. So this is an additive R action on the vector space, namely a TT, and a vector goes to e to the TA times the vector. This is an action of a group. It is a fundamental concept in mathematics. I've talked about it before. Please understand that every vector field of this linear type gives you a group action, and every group action gives you a vector field. It is exactly the same thing. And I think you will see this in physics all the time. You see these one-parameter groups acting. Some places, I said at the end of the last lecture, your vector spaces quite often are infinite dimensional. Okay? And so there's some problem with convergence. But here, e to the at, there is no problem with convergence. This is just the identity plus t times a plus b squared. A squared. Okay, and then last time I computed this out. Let me see if I can do it by memory. E to the j t is probably cosine t times the identity plus sine t times j. And that means that if you apply it to that base point above, so the base point x0 is 1, 0, what you're going to get is cosine t dt. These are in reality, the definition of cosine and sine is exactly that. So, and the way this is oriented, you're going this way around the circle, and so at time t, you have reached cosine t and sine t. Okay. By this explicit group action. Again, let me emphasize that this is really an action of something that's commuted. So that excuse me, I will write something really completely silly here, but this is fundamental. This is fundamental. And I haven't proved it for you, but you can prove it in the usual way, so it's not very exciting, right? But it is fundamental. So this is the group law that's going on in the background here. And if you apply this in this situation, so e to the t plus s times 1, 0 is the same thing as I'm sorry, I forgot j. E to the tj applied to e to the sj times 1, 0. Right? That's all I did. I used the group law that's not even hidden here. Yeah? So that is equal to that, and I wrote it down. And on the left-hand side, you can guess what you have. Well, you don't need to guess, I just wrote it for you. You will write cosine of t plus s and sine of t plus s. I just wrote it for you. Whatever you put here, you just get it. But on the right-hand side, you have to do this twice, right? And you know what you're going to get. You're going to get the addition formulas for cosine and sine, right? And you all better than I am. So this is a statement, theorem of Euler, that tells you the addition formulas for cosine and sine, whatever they are. I'm happy to do it out, but you can have much more fun doing it yourself. It's very difficult for Euler to do, because, I mean, after all, he did, if you just define, you have a circle, and you define cosine as this nut length here. I remember when I teach in high school, this is always x, and this is always y, and this is the hypotenuse, and that's always h, but in this case, the hypotenuse is 1, so it's x and y and so on, right? That was the definition. If that's your definition of cosine and sine, I don't know what you're doing about it, right? Because you can't compute it. It's very difficult to prove anything with that definition. So Euler was stuck with that, and he finally did find these power series developments. But of course, he knew nothing about convergence at that time of mathematics. The first serious convergence considerations in mathematics, in my mind, are due to Weierstrass. And Weierstrass lived in the middle to the end of the 19th century. That's not that long ago for me. Okay, so that's the thing here, and there was a comment, I think, of Mihai last time. I mean, somehow, or a question, how is this circle appearing? I mean, I've drawn the circle, but, I mean, it's a very optimistic picture, but what makes you believe that that's really true? I mean, I just wrote that down. No. But the way you understand the circle is that the norm function, which I'll just call norm for n for norm, so this is the norm function squared. I always like to square it to get a smooth function. Say norm squared. And in the standard Euclidean geometry, so the norm squared in the standard Euclidean geometry, if you just let me remind you what the norm of a vector is. Oh, let me remind you of the standard inner product. AB standard over the reals is just A1, A2, A1, B1 plus A2, B2. So this is the standard Euclidean geometry. The standard norm is just as you know it. Norm squared is just A1 squared plus A2 squared. This is norm squared. This is stupidly invariant by this function. So this is, the norm squared is invariant. So n is an invariant of the action. Okay, it's an invariant of the action. It says if you take the action and you apply something by this action, this is the action of the one parameter group. I'm writing this in general. Apply it to something. The norm doesn't care. Okay? The norm is an invariant function. Well, in a nutshell, why is that true? The reason is J is an isometry, or e to the j is an isometry of that norm. You get it? Yeah? E, these, y, so you check it. E to the tj is a group of isometry. It's a group of isometries. Now, you might have fun checking that. It occurs to me it might be a nice exercise. Okay? So let's just see how you would check it. It's enough to check that the norm is invariant, that e to the t j v e to the t, okay, I don't know, let me just do it for the fun with different vectors here, equals vw for all t and for all vw. Okay. Well, that's a horrible thing to check. The first thing you should do in an equation, friends of mine say in mathematics, an equation is a left-hand side and a right-hand side. You should make this observation. Left-hand side, right-hand side. The left-hand side is constant. Right-hand side is constant. All you really need to do to check here is that the left-hand side is constant. Because the left-hand side for t equals 0 is equal to the right-hand side. Now, through Mickey Mouse calculus, you realize that a function of one variable is constant if its derivative is 0. This is, you think this is Mickey Mouse, but if you sit down and really understand that, it's interesting. You take the derivative of the left-hand side and check it. Okay? The derivative of the left-hand side, we need to understand what that is. d dt of the left-hand side, you just do it out. Well, this is a product, right? So you use the product rule. So it's the derivative of the first times the second, plus the derivative of the second times the first. Well, I don't know, the derivative, what's the derivative of the first times the second? It's j. Maybe let's just do this, it doesn't matter. Let's just do this at t equals 0 for a convincing time. You can check the rest. So the derivative of the first is just j comes down and we evaluate at t equals 0 as j. This evaluated at t equals 0 is 1. And then this evaluated at t equals 0 times this derivative is this. Okay? Equals 0. Okay? Right? That says that J is an anti-self-adjoint operator. Right? It says that J star equals minus J. And you will see that that is exactly the condition for e to the j, or e to the tj, to be an isometry. I'm thinking, I've left some gaps here purposely. I think it's a good exercise. Okay? So to identify isometries, in this case, this rotation isometry, by the property that the operator we're dealing with, you see, you know, self-adjoint operators, what is a self-adjoint operator? It's A, B equals, so self-adjoint means A, B equals B, A, and you see here, if I bring this on the other side, it's minus. Okay? So that's the statement, this is self-adjoint. You understand self-adjoint with respect to this inner product, but means symmetric, right? With this inner product, right? So anti-self-adjoint. Okay, so that's the way you check that it is actually a group of isometries, and this is the norm in the structure, isometry group structure, so it must be invariant, and therefore the circle is invariant. The level sets of the norm are invariant. Norm 1, norm 2, and so on, they're all invariant. That means the curve has to stay inside the level set, right? And now you check that the only possible curve inside a level set is the level set itself, right? If you had some completely crazy invariant, you know, the level set of a, do you know that? He's a mathematician. Any closed set is the zero set of a smooth function. Do you know that? These physicists hate this discussion, so just don't listen. So, okay. A closed set is the opposite of an open set. If something's closed, if the other side, if the complement of it is open. And open means you can make little movements, you can stay in it. Okay. So if you give me, Abdul gives me a closed subset, you can imagine what that is, anything, yeah? Then I can find in principle a C infinity function whose zero set is exactly that set. Exactly that set. So don't tell me that C infinity functions are nice. That set is essentially any set from some point of view. You understand? An arbitrary closed subset is really, really bad. Okay? Okay. So this zero set of this norm function is, on the other hand, a beautiful closed subset. And for such closed subsets, you can say there are no curves inside these closed subsets other than the set itself. Okay? I'm seeing now I'm generating very nice homework exercises. Okay, so that's this very beautiful example. Let me give a second example of linear field. So let's let A is diagonalizable. And we're dealing here intentionally with real vector spaces, so let me first discuss the matter over R. Okay. That means, just to be careful that we know what we're talking about, i.e. there is a frame this is the frame, or ordered basis, of V over R. This is an R basis over this vector space. There are many, such that A of V j equals lambda j. So this is the usual eigenvalue situation. The real lines, you have an eigenvector V, say V1, and the action on this line is a multiplicative action by this eigenvalue lambda. So you're multiplying V1, say lambda is positive, it goes to lambda 1 times V1. It acts along this line, moving this point to this point. And down here, this is the other way around. Okay. Okay. Now let's take a base point. A base point is a linear combination of elements of this frame. Right? And you apply e to the ta to this base point. Okay. Well, that's the same thing as, this is linear, so this is the same thing as applying to these base points. All right? Well, this operator A is something complicated, but when you apply it to V1, what do you get? Lambda 1. When you apply it squared to V1, what do you get? When you apply lambda 1 times t to this thing, what do you get? Lambda t. It's completely obvious what you're getting here. You're getting the power series in the exponential function. So you're getting here C1 e to the lambda 1 t. This is really, here is a horrible thing, an operator and so on, but this is really just a function. Okay? Now, if you read elementary, particularly applied mathematics texts about ODE, they will tell you that this differential equation has n solutions. They will tell you that. And by that they mean the solutions of these on these eigenspaces. So e to the lambda 1t, e to the lambda 2t, and so on. They call these the, you're not going to hear about this. That's nonsense. It says you diagonalize the operator, and any base point can be written as a linear combination of the basis you use to diagonalize, and then on that base point, you know what the action is it's just this stuff, on these eigenvectors, it's just this stuff. Okay? Is that clear? I mean, this is something that you guys really have to know. Okay? Somebody gives you an operator, you want to understand this flow. The first step is to try a linear operator. Is to try to diagonalize it somehow or another. That's really a problem, but let's say you can do it. Okay? Then you found this basis. And any vector, any initial condition where you want to see what happens to the flow over time on this initial condition, you must express this initial vector as a linear combination of the eigenvectors, and then just follow the flow on each one of them. Okay, so let's do it. So let's take a concrete example. I have no idea how to write concrete in English. So in German, I think it's, in English it's 2 C's. In German it's 2 K's, right? Anybody know English? Right? There's 2 C's in English, right? So, concrete example in R2. Now the thing is, if you're in some vector space and these eigenvalues, God only knows how these eigenvectors are, they might not be orthogonal. There's no reason that they're going to be orthogonal, right? And so you don't know really how they're really looking in the space at hand, because you might really care for some physical reason, right? Big angles and all sorts of stuff. But if you just say, I'm just going to make that the basis and think of that as R2, then it's a standard basis. So I'm going to assume that the operator is diagonalized in the standard basis, lambda 1, lambda 2. Okay? I've destroyed the geometry of the situation by assuming that, right? Because I've moved the original eigenbasis to this basis. Well, okay. Let's look at the condition. Let's look at the situation in a number of cases depending on the signs of lambda. So if lambda 1, let's make lambda 1 and lambda 2 negative. Okay? So that means, if you want, let's write down the way you would write e to the lambda 1t, e to the lambda 2t. I don't know, just have some fun and write this in coordinates, x1, x2. It's not very hard to write this in coordinates. Excuse me. E to the lambda 1t, x1, e to the lambda 2t, x2. And then the next thing you do is you graph this thing. Okay? So the x1 axis is here. And what did I say? Lambda 1 is negative. So if this number is negative here, this means as t goes to infinity, this becomes 0, right? E to the minus 1 minus t goes to 0. And so you put an arrow like this, right? Because you see, if you start here with a point and you let it flow, I mean, this thing is invariant. So this stays invariant. It's an invariant line. You flow it to 0. This thing flows, depending on the size of lambda 2, to 0 as t goes to infinity. Similarly here, let me see here, I just discussed lambda 1. Now lambda 2 is a little bit bigger possibly than lambda 1, but still negative. So it's going to flow here, but maybe not as, let's see, bigger or no, closer to 0. So closer to 0 means a smaller velocity, right? Somehow lambda is the velocity of this field. It's constant velocity field. And let's see here if I can get this right. You're probably correct. You guys are much smarter than I, but let's see. This going faster this way than this way. So it's if I take a point here, it's going to go faster to 0 than it does here. So I think it's going to go like this, right? Right? Because it's going faster. Have I got this right? I hope I've got it right. You have to think. Yeah, it's going faster to 0 than it does coming down. So the flow is it's going to be, if they're really different, there's going to be some singular phenomena happening here. Okay? We're looking at what is called the dynamics of linear vector fields. In dimension 2, it is very simple. Here is the first simple example of a field where the origin is an attractive fixed point. We say the origin is an attractive fixed point because everything gets attracted to the origin. Okay. Well, I'll leave it to you to look at the case. This is not so hard once we mention this. Well, it's the same case, right? Because it just changes the arrows. Or if you like, changes the sign of time. It's going to be going away from 0. We say it is the origin is a repulsive fixed point. It repulses the back. So this is easy to understand. Now there's a very interesting situation which we sometimes call hyperbolic. And this is a case, let's say, where lambda 1 is less than 0 and lambda 2 is bigger than 0. Okay. So hyperbolic dynamics occur in many, many physical situations. So you really have to understand hyperbolic dynamics. There are good level sets that are invariant. So what the heck happens here? Lambda 1 has to do with x1. And lambda 1 is negative, so the flow is into the origin. It looks like that. Lambda 2 is positive, so the flow is out of the origin here. This is the case of mixed signature. Yeah. So you have what we call a stable manifold where the thing is flowing in. In this case, it's just an axis. And we have another stable manifold where it's flowing out. But if you're at the origin and you know, somebody tells you about the dynamics here, and he says, well, hey man, you go out this direction on this line, you come right back. And you say, you go out this direction on this line, and okay, you don't come right back, but you flow back at the opposite time. Yeah, but what happens here? What happens here? You happen the flow here looks like this. You go a small disturbance, yeah, and you get, here's a small disturbance, and Auf Wiedersehen, right? You go away. This is hyperbolic dynamics. Stable manifolds in and out maybe, but a small disturbance this way, Auf Wiedersehen. Auf Wiedersehen, how do you say Auf Wiedersehen in Nepalese? This is incredibly complex. What?
It's Firibetona.
Firibetona.
Yeah.
Firibetona. I don't know. Does it sound like any language you know? Is it related to anything in the neighborhood of Nepal? I mean, China is in the neighborhood of Nepal. Nepal doesn't like to agree with this, but or China also. But it's not related to any languages in India.
Somewhat related.
What, Hindu or something? Or no.
It's derived from Sanskrit, so.
From Sanskrit, so it's Very interesting. So there is a great mathematician. You see, you're a physicist, so you don't know anything about mathematics. So this was a great intellectual. He only died recently. His name is André Weil, French mathematician. But he was a great, you should read his life history, which was written in an autobiography in French, but translated beautifully in English. So, in case you don't read French, it's in English and unrejected. Among other things, he was a specialist in Sanskrit and spent much time, also, I'm sure, in your home. And his sister was also a fantastic intellectual, very liberated French intellectual woman. And so you all would like to very much learn about André Weil. He's a very interesting person. I think he only died 2 or 3 years ago. I can't remember the exact date, but not so long. Okay, so this is the hyperbolic case. you move over here nearby, and Auf Wiedersehen. So the dynamics are not stable. We say, you see, it's not at all stable. You would hope, you know. So, okay. In some sense, interesting case. Now let's do maybe one last case. How about this one? A equals this one. Ha, 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 ha. Now this operator, you want to have some fun? Let's have some fun. Compute A squared. Now let's see if you guys, you Olympiad geniuses, you can compute the square of this matrix. First row, and the first column. What do you get? Do it! I'm serious. 0. First row, second column. Well, I don't think we have to worry about the next stuff, right? This is the 0. Now, this is a fantastic phenomenon that the exponential function is really trivial, because you have the identity as the first term, right? Then t times the operator is the next term, right? Then t squared times the operator squared is the next term. What's that term? Here. Operator squared?
0.
Operator cubed?
0.
Forget it. It's an amazing thing that the exponential map, which is e to the ta, is incredibly algebraic. It stops at degree 1. This operator, because the square is 0, is called a nilpotent operator. And for nilpotent operators, that exponential mapping is wonderful. It's just this. I just write it in matrix form, right? Identity plus t, and then it quits. It's amazing, right? Just amazing. And now let's look at what happens here if I apply this thing to x1, x2. So what do you get? You get x1 plus tx2, and then just x2. We talked about this before. This is what we call, at least in English, we call it a shear. Because the flow, you see, I have a little, I have a space here. Let me draw a picture of the shear here. So it's not very good didactics, but draw a picture here. Here's the x1 and x2 axis. Here's x2 equals 0. What happens at x2, here's x1 axis. What happens here along the x, that's x2 equals 0. Right? Here's x2. You put x2 equals 0, what happens here?
Cool.
Niente. I could ask you in Nepalese, you say nothing. Okay? So nothing happens here. Right? Okay, if I go up here, now x2 is not 0. As I go along the flow, what happens to x2? Niente. Right? x2 doesn't change. That means you have this invariant manifold here. All these things are invariant manifold. Right? You start at x2, no matter how high you are, it doesn't change. Look at it. It doesn't change. Right? But what happens is there's a lot going on there, because as you move, so if I could do this in some video or something, I have little dots here. At this point you have a velocity. The velocity is x2. Okay, that's a certain velocity. Here it's a little higher on x2, so it's a bigger velocity. Here it's a little higher, it's even a bigger velocity. So do you see it? It's like a shear. It's like wind shear in some sense. Okay. We call that a shear. So that's the nilpotent operator, causes things like this. Different eigenvalues give you different dynamics. You can have fun if the operator is diagonalizable. Or almost diagonalizable. Well, this is not diagonalizable, but it's even easier to understand because there's nilpotent. Now, let me explain one last point about linear fields. not diagonalizable operators. So let's start with R2. And let's look at an operator which is not diagonalizable. And I think you would give me the first operator. So J is not diagonalizable. Over R. Okay. So you see, I taught engineering classes a long time, I taught physics classes a long time, I taught elementary math classes a long time, and I know if somebody has an operator like this, what they do. They say, well, hey man, I'm going to have some fun. I'm going to look at the determinant of Z. What do you want to do here? Z times the identity minus J. Is that what you look? Huh? No, maybe J minus Z times the identity. How about that one? Is that what you usually look at? What do you usually look at? Characteristic polynomials. Is that, would you look at it like that? Is that more or less the way you look at that? I know that all these engineering students are just incredibly intelligent, so they are able to write this down, usually sloppy, because they don't know the difference between a determinant and a matrix. So something like this, 1 minus Z minus 1. Right? Okay? And then everybody learns in kindergarten what to do here. You multiply this thing out, it's Z squared plus 1. Can you do that by memory without calculating? If you have A equals an operator, say, in the endomorphisms of R2, let me just check to see. Then determinant, the characteristic polynomial of A minus Z times the identity is Z squared minus, huh? Very good. Trace A times Z, huh? Plus the determinant, that's also a trace if you think about it correctly. Okay. So we've talked about this. The coefficients of the characteristic polynomial you're going to recover through these types of invariants. And here it's that thing. So you don't really need to calculate. You know, you don't. We're adults here. We're not engineers. Okay. So, okay. So that says in this case here, Z equals plus or minus I. Okay. I'm just following my notes, and there's nothing wrong with this. Just doing some calculations that are meaningless. I don't know what I'm doing. I'm just putting things in there and fooling around. Huh? Okay, so I say it's diagonalizable. And so this thing, e to the TA equals e to the IT, 0, e to the minus IT. It's true, right? I mean, those are the I just did it. This formula, yeah. Okay. This is what I've learned with working with applied science. Applied scientists quite often don't know some mathematical justification for something, but they really have a good feeling what you should do. So you shouldn't give up. You something like this, and you should not give up. But at this stage, you should ask, what in the devil have I done here? What have I done here? I start with the vector space over the real numbers, R2. Yeah. Here's R2. Here's R2. I have a transformation of R2. Okay. Here I'm going to dramatize it. A vector here, x, or I don't know, v, gets mapped over here to e to the t a times v. There's nothing wrong with that. We just discussed it. Oh, it's j actually. I'm sorry. Let's just do it generally. Oh no, let's do j. J. Right? And I'm trying to understand that. Now we do understand it with the circle and all that stuff, right? But I mean, let's understand it from this point of view. Okay, I'm trying to understand that. And then suddenly I did something incredible. I computed its eigenvalues, and they're complex numbers, and then I had the guts to diagonalize the matrix and get a complex diagonal. Now what did I do? What did I do? What did we do?
But you also, I mean, you also change the basis, so you cannot...
Yes, absolutely, absolutely. I didn't say anything about that.
Yeah, but that v doesn't go to a to the tjv because you change the basis of v.
V goes to e to the tjv. I mean, that's just the way the dynamical system is working. Maybe that's the vector 1, 0. We discussed it at the beginning of the class.
Yeah, but a to the tj is not that thing. You change the basis.
If I multiply this thing out, this is completely insane. I think that's what you're saying.
That is not e to the tj. It's e to the tj in another basis.
Of course, it's e to the tj in some other basis, but that's in the future of our discussion. Right now, this is just nonsense. Okay? I just had the guts to take the characteristic polynomial, to find its two roots, to write down, say, what this should be, and argue like an applied scientist and say it works. Okay? Yeah? But you must not stop there. And the good applied scientists don't stop there. Okay? What have we done? So, what did we do? So this is a vector space V. The answer to what we have done is we have complexified V. Suddenly, V is a complex vector space. Nobody tells you. Nobody tells you. They make this calculation, and they're fooling around, and under the table, they have a complex vector space, because this does not make sense otherwise. That's what you're saying. Well, Gauss also told us what to do. Gauss said, well, that's the whole thing. If you complexify something, you better add I times R2. So you have the construction of the complexification, which we might call VC, the complexified vector space. Okay. It is so, the scalars are suddenly complex numbers. I'm now allowing, instead of real scalars, you understand what I'm saying? Instead of allowing real scalar multiplication, linear combinations over real numbers, I suddenly allow complex numbers. Okay? Now, the formal way of doing this, you say you take the old vector space and you allow multiplication by the complex numbers, and that means you allow tensor product, you go to a tensor product. I'm going to explain this, but that's the meaning of that is that you now suddenly take the old vector space and you allow scalars to be complex numbers. Okay, this is a formal thing. Okay. So suddenly in this new thing, if you have a couple vectors here, v1, v2, I don't care what they are, you can take complex numbers z1 and z2, and you can take linear combinations here. And this tensor product notation means you're allowed to multiply by complex numbers vector. Okay? Just do it. It is in fact formal. Okay? It doesn't bother you if it's formal. You just, okay, complex coefficient. Does it bother you? No. Okay. Well, okay. We have complexified V. So, I have to tell you what J of a complex number is times V. Well, I'm not stupid. If J is linear in the first place, it should be linear in the second place. It should be linear. Okay? So what this says is that I have this operator J, which is somehow completely crazy from the point of view of diagonalizability. I can extend it to the complexified vector space where I'm allowed to use complex scalars. Yes? I extend it like this. I have to tell you what it, I mean, the new vectors are vector times complex number, like vector times I. So I want to know what happens when I multiply it by I here. Well, I'll just pull it out. Okay? Okay. This is purely formal. Now, let's talk about what Mihai asked about. He said, okay, now I can do this, right, because I'm allowed to multiply by complex numbers. Let's check what the basis is. That's what you were asking about, right? So let's look here. So the eigenvectors. Okay, the eigenvectors are, well, I don't know. Okay, you want to compute it? You want to have some fun? So we're looking at a vector, let's say ZW, Z1, Z2, say, times 0, 1, minus 1 equals I times Z1, Z2. Okay? Now, as I say, you guys are much smarter than I am. Come on, you Olympiad cats. So this says that minus Z2, Z1 equals I times Z1, Z2. Any ideas here? Well, let's try it. This says that Z1 equals I, Z2. And this says, okay, if Z1 is equal to I, Z2, it's a line. It's a, now, the eigenvector here, we're going to find eigenvectors here, Z1, Z2. This is the line, this is the point here. And this is the stable line through here. This is a copy of the complex numbers. It's a complex line. So, okay, now let me see, what would be a good one here? Z1 equals I times Z2. Well, it's not very hard. Let me write I1. Right? I hope that works. Can we check it? Is it okay? Z1 equals I, Z2, and the other way around would be minus Z2 equals I, Z1, but that works. Yeah, right? Because I multiply through by I, it's okay, right? So this is another one. Can anybody tell me the other one? Just like this? How did you get that?
Secret.
Huh? You have a secret? Mihai has a secret! He said minus I. Well, I agree completely. Anybody know Mihai's secret?
It's 2 abstract.
Okay, that's good. You're giving a conceptual aspect of Mihai's secret. You're saying the other one is the conjugate of this complex conjugate, right? Now, why should that be?
Because the matrix is real.
Matrix is real, right? You take a real matrix, right? A matrix is real. What about the coefficients of the characteristic polynomial? Real. What about roots of a polynomial with real coefficients? Become impaired. If you're lucky when they're different, when they're really different, I mean they could be, yeah, well, or you're unlucky. Okay. Well, what about the eigen? That was plus minus I. So I were the solutions of the characteristic polynomial. So why? Let's use these guys' arguments for the eigenvectors. Right? A, let's see here. A, can we do this? I'll do it from this way to this way. A of V equals lambda of V, my times V, right? I bar both sides. Over here I have bar of V bar times lambda bar. Here I have A bar times V bar. But A bar is equal to A and it's Mihai's point. Right? So it says A of V bar equals lambda bar V bar. So it, not only do the eigenvalues come in pairs, the eigenvectors come in pairs. Okay. So V, let's say this is V, and this is V bar, and these are the two eigenvectors. Okay? And now, the dynamics of this field is rotation V goes to e to the I t times V, and V bar goes to e to the minus I t times V. Bar. Okay. Okay? That's what we just talked about, right? Well. So isn't this exciting? You start with real numbers, and in order to do anything, you must complexify. You start with R2, in order to do anything, you really should complexify. Okay? If you were doing real mathematics, which we will try to do, you should never start with a real object. You should start with a complex object with its real points. So real things don't exist alone. They exist with complexifications, and you use the complexification. Let's just continue this discussion. I love this discussion. I'm just going to give you a little hint because I have another really nice exercise. So it's always fun to find fun exercise that everybody can do. Oh, I'm sorry. Here's it. Now, I complexify, and now I'm going to realify. There's no such word, but why not? Let's look at this vector. Okay, that's now a real vector. Let me draw my picture again. The complexification, here's R2. Here's I times R2. Here is V, and here is V bar. By the way, that's the exact picture, right? V bar is, right? It takes the positive stuff and the negative stuff. So it's a reflection across, complex conjugation is reflection across the real axis. You see it? All right. Where's V bar plus V bar over 2? right? That was fun. Right? V plus V bar over 2. That's obviously a real, what is that? That's the real part of V, right? Well, okay, what's the real part of V?
0, 1.
0, 1. Okay. Well, I had some fun here and I almost hit my old vector by just taking real parts. How could you have some more fun by some canonical operation? I mean, how do I go from complex numbers to real numbers? I take real part and? Why not take imaginary part? I don't know, this picture is really beautiful because yeah, but I don't know how to draw with imaginary part yet. So let's do it. Imaginary part of V equals, what is that? V minus V bar over 2I. Right? What's that?
1, 0.
Thank God it's 1, 0. Okay.
But who's V you started with?
Huh?
Who is V?
V is the eigenvector. Oh, what is V? I'm sorry, I was, this is true in general what I'm doing here. I see what you're saying. But here I meant here this to be, say I1. And this to be minus I1, okay? That's what you meant, right? I meant it to be the eigenvector. Okay. Here we go. Now we're going to have fun. This is the imaginary part of V. So e to the tj times the imaginary, times that, that's e to the tj times the imaginary part of this thing. Okay. Let's just be brutally formal. This is the imaginary part of e to the tj times v. Now, why could that be true? Sometimes I write something down formally and then say, can I really justify that? I can certainly justify that because the operator is real, right? And you see the operations here which determine this is this, and it's also complex linear. It's extended to be complex linear. Okay. This is sensational. E to the tj times v is e to the it times v. This is the imaginary part of e to the it times v. Right? Anybody know another? Well, that's what this is. This is e to the it times v. Imaginary part minus e to the it v. What's v? Oh, this is terrible here. I'm getting mixed up, right? I1. Maybe I don't need to do this calculation. Minus I. Probably I don't need to do this calculation. Anybody do it faster than I can? Aha.
Minus sin t cos t.
Well, let's see what happens here. The first thing, the i's cancel, right? So I have e to the it plus e to the minus it over 2. That's in the first one. And e to the it minus e to the minus it over 2i. Right? Anybody seen those things before? That's cosine and sine, right? It has to be. Right? But this is really the way to think, as opposed to power series development and exponential. Try to find the complex eigenvalues, eigenvectors. Go to the complexification. Write everything down in the complexification. And then come back to the reals, depending on what you want to do. Here I wanted to come back and understand what happened. this is what I want to understand. The way I do it is my picture here, at least for the real part. I can't draw such a nice picture for the imaginary part, but thanks very much for your attention today.